In section 9.2, we're going to be looking at systems of equations in 3 variables. So our goals are to solve systems of equations in 3 variables and use systems of variables to solve applied problems and also model the situation using a quadratic function. That's another application of systems of 3 variables. Recall if an equation in one variable to the first power, so a linear function, is graphed, what would it look like in one-dimensional space, i.e. on the number line? So if I take a look at this equation right here, if I were to graph this, since there's only one variable, if I graph this on the number line, it's going to graph with a single point as its solution. You could solve this by moving the values to the other side, dividing, and you would get a value of -3, I think. So there would be one value that would be the solution to this equation. If an equation in 2 variables, so again, this one was in one variable, there's only an x. If an equation is in 2 variables, like this example right here, is graphed, we know that it would be graphed as something in the xy plane. And I don't know exactly what this equation looks like, but I'm just going to draw something that is a 2-dimensional graph in the xy plane. It's going to be graphed as a line. So this graph up here graphs as a point. This graphs as a line. If you can think about a point turning into a line when you add another dimension, we need to think about what the graph of an equation in 3 variables is going to look like when we graph it in 3-dimensional space, i.e. this equation here, 2x plus y plus z equals 0 has 3 variables. In order to take a point into a line, we have to give another axis. So we basically pull that point up, and that point then stretches into this line. In order to graph our line in 3 dimensions, we pull our line up, and it makes a plane. You can think about a plane like a sheet of paper in space. So it's going to look something like this, but it does extend in all directions. So like a sheet of paper. For an example of what this actually looks like, I'm going to use my graphing calculator. Let me clear this one up here. We can, of course, graph our line if we wanted to. I'm going to graph in 3 space. So I need to make my calculator just a little bigger. So I can go back home in the Desmos menu, and I'm going to go into the 3D grapher instead of the 2D grapher. So in the 3D grapher here, if I type in this equation, 2x plus y plus 5z equals 0, I can see a picture of what this plane looks like and a representation of where it is in space. So according to my x and y axes, with z being the vertical axis, x and y being the horizontal axes, this would be like a piece of paper held up at this diagonal in such a way that it slopes both upward as well as north and south, east and west, if you consider those for your x and y axes. So it's an infinitely large sheet of paper is one way of considering what a plane looks like. Okay. Now, in general, we can write a linear equation in as many variables as we want, like this. We can think about it as ax1 plus bx2 plus c, x3 plus x, so on and so on, until you have n or more variables. And each of the capital letters are non-zero coefficients, and you have variables up to x to the n. It's still linear because the power on every variable is 1, so there's no exponents. And we're just going to increase the dimensions by making more variables added in. For our purposes in this section, We are going to focus on the 3-variable linear equations, like the one that we saw up here, that make the plane, like this one here is another example. We can build upon the techniques that we use here to solve equations with any number of variables and equations. Topic 1. So we're going to be solving equations or systems of equations in 3 variables. We developed some techniques in the previous section for solving two variable equations. And so we need to explore a technique for solving 3 variable equations. One of the techniques relies on the fact that if you can get down to such a form where you can solve a single equation, then you can back substitute. If you can find the value of one variable, you can back substitute that in. If you have 2 variables to find the value of the second variable, then you can back substitute those values in to find the value of the third variable. So our goal is going to be to getting equations in this form where one variable is solvable. We're going to start with an example where it's already in that form, and we're going to be able to say, take this bottom equation, and we're going to be able to solve for x. So we know that if 2x is equal to 9, then x is equal to, let's just use decimals here, so we'll say 4.5. Rather than having to keep 9 halves, since this one comes out exactly, I'm going to go for the decimal version. Then I can use the next equation, and since I know the value of x, I can plug that in, and we'll say that 3 times 4.5 minus 4 times y equals 1. Use our calculator, the regular calculator over here, to multiply that 3 times 4.5. It gives us 13.5 minus 4y equals 1. We're going to subtract that 13.5 from both sides. So 1 minus 13.5 gives us negative 4y equals negative 12.5. And again, we're going to divide by negative 4. So negative 12.5 divided by negative 4 gives us a y value of positive 3.125. From there, since I know both the values of x and y, I can plug those into the top equation to solve for z. So we'll do that next. Negative 5 times x, which is 4.5, plus 8 times y, which is 3.125, plus z equals 0. Ran out of room there just a little bit. The first 2 pieces, though, are fully numeric. So we're going to enter that and get the number for those first 2 pieces combined. Negative 5 times our 4.5 plus 8 times our 3.125. That all comes out as 2.5 plus z equals 0. So I can subtract the 2.5 off and get a value of negative 2.5 for z. So our solution is going to be an ordered triple. Ordered triples are going to be of the form x, y, z, just like ordered pairs are x, y. So an ordered triple will have the x value, the y value, followed by the z value. So 4.5, 3.125, negative 2, or no, yeah, it is negative 2.5. I looked back at my calculator and saw it was positive. That's before I subtracted it over. It is negative 2.5. So we have the x value, the y value, and the z value, and that ordered triple forms the solution. Okay. Recall that we can always do the following steps to any equations without changing the solutions. We can always interchange two equations, flip two equations, look at one equation before another. We can always multiply a single equation by a value on both sides. We can always add equations together. This is dealing with the elimination method. So this method of Gaussian elimination is a method of elimination similar to the elimination method from section 9.1, but it's built for equations that are in three variables. To work on this elimination method, we're going to choose one of the variables to eliminate, and we're going to eliminate that in two different pairs of equations. Eliminate that same variable in two different equations. By doing that, you are going to create a new system in which you have two equations that have only two variables. From there, you can solve the system using the same techniques from 9.1. You can use the elimination method if you want, or even the substitution method. You're going to take your two variable equations and eliminate another variable, and that's going to leave you with a single variable. Solve for that single variable, and then back substitute into the two variables to get the second variable, and finally back substitute into the first equation to get the third variable, and you'll have your system solved. The final bit of advice is it's always nice to check your solutions so you can check them. And if at any point you end up with a redundant equation, such as 0 equals 0, then you're going to conclude that those two equations are dependent. We can remove one of the equations without affecting the solution, and we will have an ordered triple that's going to be in terms of one variable for our solution. Or if at any point in the process we have a false equation, like 0 equals 5, redundant meant true, false not true, we can conclude that the original equation is inconsistent and therefore has no solution. So we'll have to watch out for those two special steps as things that come out without a singular solution. We did get a singular solution, of course, in example 1. Okay. We're going to take a look at, I guess, example 1 again. So the next example here. And there are three equations to work from. The first one is x minus 2y plus 3z equals 11. We've got 4x plus 2y minus 3z equals 4. And the third equation is 3x plus 3y minus z equals 4. Take a look at all of your variables, x, y, and z, because you're going to need to eliminate the same variable twice. For x's, 1, 4, and 3, I could work 1 and 4 together or 1 and 3 together pretty conveniently. For y, I can do 2 and 2 or 2 and 3 for 6. For z, I can do 3 and 3 already, or 1 and 3, make those both 3s. I think out of all of those choices, I'm going to eliminate the z's because it's going to involve the smallest amount of change. So I'm going to get rid of the z's. And I'm going to first get rid of the z's with the top two equations, because with those two equations, I don't need to change anything. I'm going to keep positive 3z and a negative 3z, and we're going to add those to get rid of z. So leaving alone x minus 2y plus 3z equals 11, and then 4x plus 2y minus 3z equals 4. My goal is getting rid of z. So let's add the two equations up. X plus 4x is 5x. Negative 2y plus 2y adds to 0y. And then the goal here was eliminating z. Negative 3z plus 3z adds to 0z. So my goal wasn't to get rid of y, but I happened to do so, and that's not a problem. And I end up with 11 plus 4, which is 15, I end up able to solve for x right away. So I can divide by 5, and I'll get a value of x equals 3. So I've got one of my variables right from the get-go. That's fortunate. It's lucky. That's not always going to happen. Now I want to take the next two, and my goal was to get rid of z, so I'm going to do that again. Noticing that this z is negative, instead of working with a negative 3z, I'm going to work with the positive 3z and the negative z. I'm going to need to just multiply this bottom equation by a 3 so that I will have both a positive 3z and a negative 3z at the end. So if we do that, the top, no change is required. It already has the 3z. So I'm going to leave x minus 2y plus 3z equals 11. When I multiply by 3, that's going to be 3 times 3 is 9x. 3 times 3 is 9y. 3 times negative 1, negative 3z equals 3 times 4 is 12. Now you can see that it can be difficult to organize your steps right here. So I'm going to number my steps as step number 1 and step number 2, just to try to keep track of where I'm going, because I'm going to probably wind around my page a little bit here, just using up the space. Let's add our two equations together. X plus 9x is 10x. Negative 2y plus 9y is 7y. And then as designed, 3z plus negative 3z is going to eliminate, add to 0z. And this will equal 11 plus 12 is 23. Typically at this point, I would have two equations that both had x and y, but don't have a z, and so I should be able to use these two equations to solve. I'm even more fortunate right now because I know the value for x. Because I don't have a z here, if I use this value for x, plugged in for x, I'm going to be able to solve for y. So we're going to do that right here in my step number 3. We're going to plug in our 3, so 10 times 3 for x plus 7 for y equals 23. So that's 30 plus 7y equals 23. So 7y is going to equal negative 7 if I subtract off the 30. And if I divide by 7, y is going to be equal to negative 1. Now that I know both x and y, I'm going to plug those into any one of the original equations to solve for the z value. I'm going to go ahead and choose the bottom equation strictly because the coefficient of z is smallest and that's the one I'm solving for. It doesn't matter though, I can use any of these. So that's going to be our step number 4. Plugging the values for both x and y in the equation for x and y and solving for z. So we'll have 3 times the x value, which is 3, 3 times the y value, which is negative 1, minus z equals 4. That's 9 minus 3 minus z equals 4. 9 minus 3 is 6. Minus z equals 4. Subtracting the 6 over gives us negative z equals negative 2. Dividing by the negative 1 will give us z equals 2. So we've got ourselves the z value. We now know that our solution is going to be the ordered triple with x value 3, y value negative 1, z value 2. Is this set consistent and is this set independent? I did get a solution, so we know this is consistent. And I did not get that the two lines or two planes were going to be identical, so I know that they are independent. When you get one and only one ordered pair solution, you are both consistent and independent. All right, let's take a look at another example. There are, again, three equations here. The first one is x plus y plus z equals 7. The next one is 3x minus 2y plus z equals 3. And the next one is x plus 6y plus 3z equals 25. Looking at all three of the variables, we've got x, 3x, y, 2y, 6y, z, 3z. It looks like getting rid of either x or z is pretty equal since I have just coefficient 1 and then coefficient 3. So it doesn't really matter to me if I get rid of either x or z. Since I got rid of z last time, let's go ahead and get rid of x. They're in the fronts right here. We've got some really convenient coefficients to use. I'm going to start by eliminating x in the first and last equations because I can do that with coefficient 1. I'm going to want to multiply one of these by a -1. So if we just look at the rest of the equation, it's going to work better if the smaller number is negative. So I'm going to multiply the top equation by -1, and then we'll add these two equations up. So for step number 1, I'm going to have -x minus y minus z equals -7 when I multiply a -1 through the top equation. Bottom equation, no change. So that's x plus 6y plus 3z equals 25. Add our two equations up. The goal was to eliminate x. -x plus x does add to 0, so there are no x left. -y plus 6y is 5y. -z plus 3z is going to be plus 2z. And -7 plus 25 is going to add to 18. All right, so we were able to eliminate x as we wanted. We've got an equation that has just y and z. We need to get rid of x another time. So I need to work with the equation I didn't use, and I can work with either this equation and the bottom or this equation and the top. I would like to use the smaller numbers again. So this time I'm going to use the top and middle equations. For the top and middle equations, I need to make my coefficients both 3's. If this one's a 3, I'm going to want to make the top equation have a -3 coefficient. So I'm going to multiply the top equation by -3 and leave the middle equation alone. So in my step number 2, top equation by -3 will make it -3x minus 3y minus 3z equals -21, multiplying everything by -3. Middle equation, because it already has a positive 3x, will stay the same. 3x minus 2y plus z equals 3. When we add these, -3x plus 3x adds to 0. It was our goal to eliminate x. That's on track here. -3y minus 2y is -5y. -3z plus z is -2z. And -21 plus 3 is -18. What we should do next for step 3 is work on these two equations together. We should be working on eliminating a variable from both equations that are in only y and z. Neither has an x. The two variables they have are y and z. So if I'm going to check these out, I want to eliminate either the y or the z. Now I can already see that I'm leading up to a situation where both are going to eliminate. But let's write them down. We've got ourselves 5y plus 2z equals 18. And we've got a -5y minus 2z equals -18. If we add up our two equations here, add 5y minus 5y adds to 0, and 2z minus 2z adds to 0. So the entire left side adds to 0. And on the right side, negative 18 plus 18 adds to 0. So this is a true statement, and that's going to lead us to one of the dependent cases. Since it's a dependent case, we had the same two things right here. We can write our solution by solving for either y or z, one of the two remaining variables in one of these equations. It doesn't matter which of the two equations we use since they are the same thing. Analyzing this to look at the coefficients for y and z, 5 and 2, I'm going to choose to solve for z just because it has the smaller coefficient. So on step number 4 here, we're going to take, let's just use the one that has the positives. Let's solve the 5y plus 2z equals 18 for, and we can pick, so we're just going to choose z. So if I solve this for z, 2z would be equal to negative 5y plus 18. I almost wrote 9, so I was thinking about dividing by 2, which I have not done yet. We're going to divide by 2 next. So when I divide by 2, z would be equal to negative 5 halves y. Now it's plus 9. I needed to divide by 2 and distribute that 2 across both terms. So z is equal to negative 5 halves y plus 2. Again, it doesn't really matter which variable I solve for, but I'm in terms of y now. Now that I'm in terms of y, we're going to have to use y as the dependent variable and try to discuss both x, y, and z in terms of y. So this is now in terms of y. So our goal now is to solve for x in terms of y also. So we're going to solve for x in terms of y. So we're going to take one of our equations. We're going to go with the one that has the smallest coefficients. So it's going to be the top equation. We're going to solve for x in terms of y. The top equation was x plus y plus z equals 7. I do need to get rid of z, but I know what z is equal to, so we'll replace that right away. X plus y minus 5 halves y plus 9 equals 7. If we combine like terms, x is equal to 1y minus 5 halves y. 2 minus 5 is negative 3, so that's negative 3 halves y. And if I subtract the 9 to the other side, that's going to be equal to negative 2. Adding the 3 halves y to the other side gives x equals positive 3 halves y minus 2. So our ordered triple, which is of the form x, comma y, comma z, is going to be equal to x, which is 3 halves y minus 2, comma y is y, comma z is negative 5 halves y plus 9. So this is the solution in terms of y. I don't have a number solution, but I do have a format for the solution in such a way that if I know or give a value for y, I could make a table of values for the others. Let me take a look at what I'm talking about here. I think I can do this with a table, so let me make a quick attempt here. Let me make a table, and in this table, the x value would be 3 halves of the y1 value minus 2. the y value is going to stay y, and the z value would be -5/2 of the y1 value plus 9. So if I plug in values for y1, like 0, 1, 2, 3, 4, 5, and so on, I will be able to make a grouping of ordered triplets. Ignore the graph that we're seeing on the side right here because these points would graph as ordered triplets. So they would graph in a 3-dimensional grid, not a 2-dimensional grid. But this is just some of the ordered triplets that would be solutions to this particular graph. On the next page, we're going to look at visualizing these solutions. Up to this point, we have been skirting the boundaries of algebra and geometry, using equations to describe some of our spatial relationships. As we noted on the first page, an equation in one variable graphs as a point in one dimension. An equation in two variables graphs as a line in 2 dimensions, and an equation in 3 variables graphs as a plane in 3 dimensions. We already know what happens when we solve 2 equations in 2 variables. We discussed that in the last section. So what happens when we solve 3 linear equations in 3 variables? The graph can result with a single point and the coordinates are going to be x, y, z, whatever those numbers for x, y, and z are, as the solution. Or, so we can see there are 3 different planes right here. I'm going to draw some planes like this in Desmos in just a minute. These ones are hard to see because their font, their color. I'm going to outline them here. This is one of the planes. The other plane is here. And the final plane is here. So those 3 planes are intersecting in one point. Or these planes are forming like this tent shape where there's this open triangle in the middle. So 2 of the planes intersect in a line. These 2 planes intersect in another line. And these 2 planes intersect in yet a third line. But all 3 planes don't intersect anywhere. So in this case, there would be no solution. All 3 are never equal. Or all 3 could be completely parallel. So in this one, any 2 intersect, but all 3 never intersect. This case also has no solution. All 3 are parallel and there are no intersections between any 3. And then in terms of many solutions, in this case, all 3 intersect in a line. So all points on this line are solutions. Or all 3 planes could be identical. So the intersection is a plane. all points on the plane are solutions. So let's take a quick look back at those two that we had solved a moment ago using the 3D grapher. So I'm going to clear. The first one that we solved was a system that had x minus 2y plus 3z equals 11. Then we had 4x plus 2y minus 3z equals 4. And we had 3x plus 3y minus z equals 4. So we can see from our graphs right here that these are all intersecting in one point. And we did solve for that point, and we saw that it came out as the ordered triplet 1, negative 1, 2. And so if I graph that point, I'm going to change it so it's, I guess gray is fine. I can see that point right there is the point of intersection. It's that little ball right there is the point of intersection. So we can verify that we have a type of model where we have 3 distinct planes intersecting in one point, as according to our solution to the first one. Let's see what happened in the second one. In the second one, the equations x plus y plus z equals 7, 3x minus 2y plus z equals 3, and x plus 6y plus 3z equals 25. This is the case where there's a line that is the solution between these 3 planes. They meet not at one point, but across an entire line. Our solution down here in this ordered triplet in terms of y is the parametric equation that will express that line. Unfortunately, I'm not able to graph this equation in parametric mode using the graphing calculator right here, but just know that that is what this is doing for us. So by getting this equation right here, this is an expression of a line that is a solution. This is the parametric equation for a line that is in 3 dimensions. Okay. All right, so let's take a look at our final page here. We're looking at an application. It says there are many ways to apply the method of 3 equations in story problems. As usual, the translation from words to mathematical equations is usually the hardest part of this technique. So let's read through this situation carefully and write ourselves some equations. A private club has $200,000 earmarked for investments in stocks, and all of it has to be invested. To arrive at an acceptable overall level of risk, the stocks need to be or have been classified into 3 categories. We're going to have high risk, medium risk, and low risk. Management estimates that high risk stocks, I'm going to color code these differently, so high risk stocks are going to have a return rate of 15% per year. Medium risk stocks have a return rate of 10% per year. And then low risk stocks have a return of 6% per year. The members of the club have decided that the investment in low risk stocks should be equal to the sum of the investments in stocks that are in the other two categories. Determine how much the club should invest in each type of stock to have a return of $20,000 per year on the total investment. Okay. I'm going to use the variables x, y, and z. X is going to be the amount that we're going to invest in the high risk category. X amount invested at high risk. Y is going to be the amount invested at medium risk. And I'll use Z as the amount invested at low risk. Okay. One of my equations is going to deal with the fact that we have $200,000 earmarked for investment in all of the stocks. So we know that if we look at all that we invest, X plus Y plus Z, we're going to have a total of 200,000 invested. As far as the returns, high risk returns 15%, medium risk returns 10%, and low risk returns 6%. The percentage return, if I add up the amounts returned, is going to equal $20,000. So for high risk was 15%. So 0.15, 15% times the amount invested at high risk, plus medium risk was 10%, 0.10 or 0.1 times the Y, the amount at medium risk, plus 6%, 0.06 of the amount invested at low risk would equal the total return, which is going to be $20,000. So make sure that's the 200. I'm going to put the comma in for right now. 200,000 is the total amount invested, and this is the $20,000 for the amount returned. And our last bit of information is that the amount in low risk should equal the sum of the investment in the other two categories. So I'm actually going to write that up here for a second. The amount in low risk, that is Z, should be equal to the sum of the other two categories. Z should be equal to X plus Y. And I wrote that up here because my equations need to be lined up, and this one's not, but I can subtract the Z over and write this as X plus Y minus Z, and it would be equal to 0. So we have ourselves a system of 3 equations and 3 variables, and we've got it lined up so that we can see our X's, our Y's, our Z's, their coefficients, as well as our constants. Okay. In choosing a variable to get rid of, I can choose any, of course. I'm going to go with Z because there's already one negative, so I'm going to have less sign changes to work with. So I'm going to start with the top and bottom equation as is because the Z's are already ready to eliminate. So in my first step, we'll take X plus Y plus Z equals 200,000. And X plus Y minus Z equals 0. If we add this up, we'll have 2X plus 2Y equals 200,000. In step 2, we need to get rid of the Z variable again. I'm going to go with the middle and bottom equation this time because, again, I have a negative already here. But I need the 0.6. So I'm going to multiply by 0.06 on the bottom equation so that I can add those up and the z's will eliminate. Middle won't change. It's going to stay 0.15x plus 0.1y plus 0.06z equals 20,000. When I multiply by the 0.06, I'll have 0.06x plus 0.06. I'm going to move the decimal place there so I don't have the extra 0. 0.06y minus 0.06z equals 0 times 0.06, which is still 0. When I add these up, 0.15 plus 0.06 is going to add up to 0.21x. 0.1 plus 0.06 is going to add up to 0.16y, and then the z's eliminate, add to 0, and 20,000 plus 0 is 20,000. We've got our two equations here. We need to solve this system. I'm going to go ahead and manipulate this equation right here to solve for x or y. I'm going to use substitution to solve this two-variable system. So let me solve for x. So x is equal to, well, I'll start with the 2x. 2x is equal to negative 2y plus 200,000. So x is equal to negative y plus 100,000. In step 3, I'm going to plug that in for x. So 0.21 times negative y plus 100,000 plus 0.16y equals 20,000. If we distribute, that gives us negative 0.21y plus 21,000. 0.21 times 100,000 plus 0.16y equals 20,000. I'm going to subtract the 21,000 from the 20,000. So that should give me a negative 1,000 on the right-hand side. And over here, negative 0.21y plus 0.16y is going to give us a negative 0.05y. Okay, so to our calculator, we can definitely have done any of those calculations on the calculator. Hopefully my mental math there was sufficient when adding up the coefficients, like our 0.05y there. We're going to now divide the negative 1,000 by the negative 0.05 to get us the y value of 20,000. I've got the y value, so we need to find the x and z value. So in step 4, I actually already know that x is equal to negative y plus 100,000. So that would be negative 20,000 for y plus 100,000. So that would have to be 80,000. And then for z, I know that x plus y plus z is equal to 200,000. So 80,000 plus 20,000 plus z equals 200,000. 80,000 plus 20,000 is 100,000. plus z equals 200,000. So if I subtract off 100,000, I should get a z value of 100,000. So in conclusion, we need to invest X 80,000 at X was high risk. We need to invest 20,000 at medium risk. And we need to invest 100,000 at low risk to get the returns that we were hoping for.